Okay, so why do you need such a technology like retrieval augmented generation? And the short answer is because large language models don't have the latest data, and also might hallucinate if somebody is asking or prompting a question for which the large language model was not fine-tuned. And this can be very dangerous for critical infrastructures. So that's why we need to augment large language models with an external database we can trust, and to help the large language model to provide us an correct answer based on data which is originated from our own trusted data. So retrieval augmented generation basically means that we have three big steps. First one is retrieval, which means that we need to search throughout our database, again, our own trusted source of truth. We need to search for relevant data whenever we are asking a question. Then our question, together with the result of this search from the database, goes to the large language model. So here, why the what the second letter means, A, augmented. Augmented means that our prompt, our question, is augmented with information from this database, which basically are represent the answer to our question. And for the third step, this augmented prompt goes to the large language model. So the large language model receives our query, but it's not an isolated query. It is a query which now has a context, and the context is made of all this information from our database, which means that the process of retrieval from the database and the quality of the database itself is super important, because this is what goes to the large language model, and this is the information used by the large language model to answer to our query. So in this way, we eliminate the hallucination problem. And the second issue with the large language model is that um, they are trained with, let's say, data which becomes old in time. If there are any questions, please interrupt me, and I will try to answer them so far.
How large can one of these databases be?
Sorry, Chris?
How large can one of these databases be?
Well, this database can be as large as you need. So this database basically can be, let's say, your internal enterprise repository. So it can be, in theory, as large as you want. Now, the question is, how do we organize these databases and how we retrieve relevant data from this huge database is a different question. But the answer to the question is as big as you can.
Yeah, I guess my real question was the second part of what you were answering, is how do you limit the amount of data given that the context window is limited?
So basically, not the context window is the limitation or the challenge here. The biggest challenge here is if you have a big database and you want to find an answer to a particular query, a particular question, the biggest challenge is how can you be sure that you retrieve your answer from a huge database, because the answer of your question can be distributed across your database in hundreds of places. How can you be sure that you get access to these all these pieces in order to have the complete context for your question? This is the question basically. The amount of this limitation related to the context window is secondary. Okay, so I will come back to the second part of my answer, which was how can we make sure that we capture or we retrieve all the relevant data from our database, which will be part of the advanced RAG techniques we need to employ in order to extract all the relevant and useful data from our huge database. Okay, so as mentioned, we need to use RAG because of its two, let's say, architectural limitation of large language models, which have these two effects, which is hallucination and lack of private information. By design, a large language model, let's say a public large language model, cannot have, or by definition, a public large language model cannot have private information. So another thing is, as you know, a large language model is a statistical machine at the end of the day. Yeah, a large language model does not know facts. It just predict a next token, which means that in order for us to be sure that a large language model or a AI system, let's say, provides us a trusted answer, we need to use a trusted source of data, which is external database. Again, by design or by definition, a large language model, a public large language model, I want to emphasize this because I'm going to challenge the authors of this book. So by design, a public large language model cannot contain private data, hopefully don't contain private data, which means that if we want to interact in any way or shape with our private data, which can be a huge database, we need another mechanism. So, and that mechanism is RAG. Here, the authors claim that we don't need to constantly fine-tune a large language model on the new data, even private data, and they claim that this process is expensive. Probably this was true at the date of publishing this book. Nowadays, I want to challenge actually this idea that it's expensive to make your own large language model. Because nowadays there are so many libraries and very, very cheap methodologies to create your own large language model with your own data and to host within your premise. So the argument that it's expensive to fine-tune a large language model is no longer valid. Okay, so the authors start with framework, which is retrieval augmented generation. They start using a vanilla or a naive, how is it called, a naive framework. Naive means that it's really naive by all definitions. So, but it's important to understand the overall flow and the overall flow of data and the overall logic of a large language model using this vanilla RAG. So, so any RAG system has three components. First one is ingestion, which means that data should be somehow ingested, either streaming or using batches. It doesn't matter. We need a database, so we need this step, ingestion. The second, which is by far the most important, is the most important step, is retrieval. Retrieval is the capability of the algorithms to extract relevant pieces of data within this database. At the end of the day, we want to make sure that the extracted data from the database provides a complete and correct answer to our query. The generation pipeline or the generation component of RAG is the most is the simplest step, the least relevant, I should say, is basically just a matter of formatting which is done by the large language model. And basically, this is what large language model excel at writing beautifully and creating, let's say, nice. But the content provided to large language model makes the difference, and the content is what comes from retrieval. Here a description of how the process, how these three components work. So a user, a client, asks a question. In the ingestion pipeline, assuming that ingestion pipeline already populated a database, this question is used by retrieval model to find relevant pieces of answer to this question. And the question, together with the pieces of the answer coming from the database, which represent basically the context for the large language model, are sent towards a large language model. And the large language model will take into account this context, which comes from the database, and will respond to the question, which is part of the prompt. This here is depicted in this diagram. So we have various data sources. For example, for an enterprise, we have policies, we have SharePoint, we have databases, CSV files, etc. So all this data should go through a cleaning process. So then we need to chunk all this data in certain sizes. Here, one comment is that the size of the chunks is more than an art than a science. So it's based on trial and error. So based on my experience, chunking size is super important in this process, and it implies a deep understanding of the data. And all these chunks then are embedded using various embedding models. I will, again, I want to emphasize a little bit the embedding because it's super, super important, this step. So when the user is, okay, so all these pieces, all the chunks, together with the metadata, which is a pointer to the original documents, are saved within a vector database. There are tons of vendors, a lot of vendors, which are selling various for this capability, which is vector database. So when a user here on the when a user is here on the bottom right is asking a question, basically provides an input. This question goes to the same embedding model, and basically the user question turns into a vector. And now the magic happens within the vector database. This vector, which represents the user question, is checked or verified against all the other vectors, which are the representation of each chunk, to find the similarity search. Basically, what happens is a cosine function applies between the user input, the user vector, I should say, and every other chunk within the vector database, which is also a vector. And the closest or the most similar chunks are those which have cosine function close to 1, because cosine of 0 is 1. So from this vector data, we select k number of chunks which are the most similar to the user question, and these chunks are sent. These chunks, k can be a fixed number from 1 to any number, and these chunks represent the context to the user query. So all these K documents, together with their metadata, together with their user original question and with a prompt template, if we use a prompt template, become, let's say, the big question for the large language model. So the large language model will consider all these K documents, these K chunks, which are the closest, mathematically speaking, to the user query. So that consider these K documents as the context for the question, for the user question. And the large language model will generate an answer exclusively based on these K documents. So, and in this way, we solve the problem of hallucination. So we are 100% sure that the large language model will not make up anything, will not predict any next token or something, but will reorganize, organize and will create a beautiful answer, let's say, to our question, exclusively based on the chunks extracted from the vector database. If there are any questions to this part?
I have a question. It's a continuation of my last question, and let me phrase it better. So the context window, it constrains the amount of information that you can process with the model. That's just, we can agree with that there is a constraint. Okay. So my question is, a lot of times when I'm asking a prompt, my prompt will also include documents that are relevant to my prompt, which takes up space in that context window. And my previous questions take up space in that context window as they're related to my current question. And so what I'm trying to understand is, in terms of retrieval, there's a finite amount of things that can be retrieved based off of this constraint, and it's further constrained by K, is what I'm here. You can only retrieve a certain number of chunks. What I'm trying to understand is the balance between the size of my prompt, the context window that I'm bringing to the table, and then how am I squeezing all the chunks from let's say a very large data set that has many relevant chunks to my question. How do we programmatically limit the number of chunks that come in, given that my prompt itself will vary in size? I'm trying to understand, how do we do that programmatically? I don't know.
Okay. Okay. Let's see if I get it right. So let's assume that the context window for a large language model is 1,000 tokens. Let's make an example. 1,000 tokens. Let's say K equal 5. In this example, K equal 5. It's a finite number. So that means that, and let's say the question, the user query will have, I don't know, 100 tokens. That means that the budget for the context will be 900 tokens. 900 tokens divided by 5, by K, means around 200 tokens per chunk. So, which means that when we chunk, and so there are multiple elements here. Of course, there are some trade-offs which we need to take into account. But at the end of the day, as we said, it's mathematics. So we have a budget for the context window, and we need to fill in this context window with relevant data from our vector database. So we need that based on this amount of, based on the context window, we decide, we factor in this information when we decide how big is the chunk and how many chunks, what is the value of K. So the chunk size depends on the data type. For example, if we have a PDF, a book, then let's say only with text, then a chunk will be a paragraph, for example. If we have a CV, a curriculum vitae, then the chunk will be probably just 2 lines from the CV. If we have code from GitHub, the chunk should a chunk within a chunk we should get a big portion of the code, which is let's say which does certain functions. So assuming that we know the type of the data, so let's say a document, a book, assuming that we design correctly the value of the size, the chunk size, then we can compute what should be the amount of chunks we can send over to the large language model. Definitely, we will lose precision because we need to make a trade-off. So if the answer, let's say, if a complete answer from our document will be made of, I don't know, 100 chunks, but we are able to send to our large language model only 5 chunks, it's a trade-off. So we need to either to maybe change the large language model to support a bigger change context window, for example, or we need to reformat somehow the data to allow for smaller chunks. So again, I think from my experience with RAG, I think it's very important to have an intimate relationship with the data, to understand the nature of the data, and then, of course, all these technical factors which constrain the quality of the output. It's a trade-off. Assuming that we have an infinite context window, whatever infinite means, then this problem does not exist anymore. But in real life, the context window will always be bounded to a value, and the number of chunks, or the size of the prompt, basically, the size of the context. The size of the context will basically will provide us a better or worse answer to the question. So the context to something is basically so the quality of the answer is a function of the relevance of the context.
Yeah.
So if we can provide a context which contains everything related to the query, to the user query, then the large language model will provide the perfect answer. If we don't, because of technical limitations, finite context windows, or then we need to make some trade-offs. We should be very aware of them. I mean, we should know what we give up to in order to work, or in order to provide a certain latency. Or so it's a trade-off. It's a trade-off between parameters.
I think it's a good question. One thing I just add is there's not a simple answer. You know, when you design it, it depends on. It says you must adopt various chunking strategies based on basically your needs. So it also says that you have to ensure that the chunk size doesn't exceed the maximum input size of the embedding model. And so then it goes into a long dialogue, and it shows different concepts of how it could be influenced and how you could change it and how we did it in a simpler way. And then it keeps on jumping back and forth. There's no one simple solution. And it's just simply, you have to be mindful of it and make sure your system is either going to be streaming or batched, and then make sure you implement various chunking standards that don't exceed the embedding requirements. So there's no one answer, but it's something that you have to be mindful of as you design it.
I think that the answer to my question is that there is no dynamic chunking or dynamic selection of K. That's
no.
That's not programmatically done. That's more of the art of setting these up. And you really hit it, Eddie, when I understand. I was looking for maybe there's a dynamic solution to it, but thank you. I get it.
Yeah, but again, this K part of the answer, naive approach to RAG. There are more sophisticated RAG frameworks which their K at all. So K exists in this, let's say, naive approach. Another one of my favorite advanced RAG methodology is called Raptor. And basically what it does, it allows you, and now I can answer to the, I think, Chris question about the size of the database. So you have, let's say, 1,000 documents. So using Raptor, I will share the link later. So using this advanced RAG technology, let's say these 1,000 documents are organized, are clustered based on their data type and their content. And this, for every cluster, we use a large language model to create a summary. And then we create another level of clustering. And basically, we create out of 1,000 documents or 1 million documents, we create a tree structure, yeah, using clustering. And then when you ask a question, then the answer will always follow a certain pass within this tree. So here K does not exist anymore, so we don't care about K. K exists, as I said, in this naive approach. So there are other RAG techniques. There are 30 or 40 I'm aware of. I will share, it's a paper which documents all of them. So I will share all the advanced RAG techniques. Every advanced RAG technique addresses a certain use case. So that's why you need to understand. Of course, you know what you know your problem you want to solve, but you need to understand how advanced RAG methodologies solve this problem from various angles, and to find your best, your best methodology. Advanced, again, and underline this idea, advanced RAG methodology for your use case. What I'm showing here is it's a naive, really, literally speaking, it's a naive implementation, and K, it's the biggest limitation, because if you extract top K, whatever K is, you can have very important parts of your answer below this value or beyond this value. So you never know about that. So, but again, at the conceptual level, these three levels or three step architecture and this simple diagram, which is shared by the authors, it's important just to understand the concepts. But it's not, this architecture does not work in reality. I tell you, I tell you from my experience, this architecture does not work. It's just for conceptual understanding. Okay. If there are, let's move forward. Okay, so this is the basic architecture from RAG. Here the authors go through the ingestion pipeline, and the most importantly, as I said, the most important step within the within this ingestion step is embedding. And chunking, embedding and chunking, these two steps, which are super important. Why embedding is important? Embedding is important because it has, I don't know, for me, it has implication at all possible levels I can imagine, starting with philosophy, psychology, theology, mathematics. So this embedding is super critical, probably the most critical process in the entire AI architecture. So it's critical because it has to do with meaning. And meaning, it's not a trivial concept for anything. And meaning of a word, it's not, or meaning of a concept, it's a very difficult thing, in my opinion. Now, many people say that embedding is computing the numerical representation of words or concepts, and which represent their meaning. I would argue this, let's say, school of thinking, because I think embedding is only making is only taking care of the relationships between concepts, because I don't think or I cannot understand how can a word like Coca-Cola, for example, or an apple can exist isolated. So in order to compute an embedding for something, we need to put it within a bigger, let's say, framework, within a bigger context, and then to say that an apple is closer as a meaning to an orange than it is to an BMW, for example. So the embedding component is so important because it captures the mathematical representation of the relationship between words. It's a deep topic for me.
I totally agree with you, but I think what they're getting at about given words numerical value is not just numerical value, but without doing this, you cannot run the calculations necessary for backpropagation.
Yeah, absolutely. I mean, in order to feed in some data to a neural network, we need to turn it into numbers. So we need numbers. We need numbers because otherwise we cannot work. I mean, the neural networks cannot work with words. The neural networks can work with numbers, with tensors, with matrices. So we need this conversion anyway. The question is, how do we make the conversion from words to numbers? And what is the relationship between a word and a vector? So this was the question I tried to rhetorically answer. Okay, so second, and the second, as I said, the second important topic is this chunking module, which splits the document in smaller ones. And I will share with you a list with all the embedding models and what are their size. Okay. The second part of the architecture is the retrieval pipeline. Again, it's super important because basically this pipeline or this part of the architecture gives the answer to our question, literally speaking. This is the, let's say, encodes the Google search, encodes for our question. And if we don't get it right or complete, or then the large language model will work with what we provide or what this retrieval pipeline provides. So that's why it's super important. So cosine here, it's one method to compute how a question is related to a chunk. A chunk is a piece of the text, which we can think of a chunk like a piece of the answer. So if the answer is a complex, let's say, sentence, a chunk is a piece of that sentence. It's just of the phrase. So the user query is turned into a vector using this numerical representation embedding, and this vector is compared with all the other vectors within the database, and whoever chunks / vectors have the biggest value in terms of cosine with the user query, then that means that their meaning is very, very close. So it ranges because cosine ranges from -1 to 1. -1 means that vector A, which is the user query, for example, and B is a chunk within the database are in opposite directions, so they have nothing to do with each other. 0 means that they are orthogonal, so there are some relationship, but 1 means that they are pointing in the same direction, and the user query, which is vector A, and the chunk, which is vector B, are pointing to the same direction, which means that they are related, and vector B will be part of the answer. Generation pipeline, as I said, is the simplest and easiest one, the least relevant for the architecture, because here the large language model just take in the user query and the context, which is the sum of the chunks, relevant chunks, and creates a nice and beautifully expressed answer. Of course, we can apply various templates in this stage. We can provide a system template. We can provide a prompt template to further, let's say, shape the answer. But it's from my point of view, it's a cosmetic or almost cosmetic let's say, aspect which is done by this at this stage. Okay, embeddings again. I mean, yeah, here the authors are explaining the how the embeddings work and what they represent. Again, here I consider that embeddings have to do with the relationships between words more than absolute meaning of a word. So that's why the way in which we embed things is super important. In this simple representation, he introduced, or we plug in these three words into our embedding model, dog, cat, and house. And we will get three vectors. The size of the vector it represents the dimension of the embedding model, which can vary between, I don't know, 64 to 4,000. I will show you the latest graphs from Hugging Face. So basically, this is one of the strengths of large language models. The embeddings represent one of the biggest strengths by far of large language models, because using this mathematical representation, we can extract out of a simple word, we can extract thousands of characteristics, potentially thousands of characteristics. It's not possible for a human being, or a normal human being, to describe a cat, for example, using, I don't know, 2,000 characteristics. It's simply not possible, or probably, I don't know. But for a mathematical model, for an embedding neural network, an embedding model, this is not an issue. And that means that the degree of detail and sophistication for the numerical representation is very, very high, which exceeds the human capacity of mapping or matching words or meaning of the words. Here the authors describe different algorithm used for dimensionality reduction. Obviously, the big number of dimensions makes impossible to visually represent these vectors, because our human limitation is only in 3 dimensions, x, y, z. So this is the maximum number of dimensions we can perceive as humans. So we can represent a number in 3 dimensions, and that's all. But with the embedding models, a word can represent it with 2,000 dimensions, for example, which is impossible to visualize for us. So that's why various techniques like WMAP or PCA are employed to reduce the size of the vector to 2 or 3, which can be easily depicted on a paper or in space, with the condition that we take the most important components within that vector, because we don't want to get rid of the most important or most meaningful parts of the vector. So if let's say a word is depicted by a vector with 1,000 dimensions, and every element within this vector has or describes a characteristic of that word, then if we need to simplify these 1,000 dimensions to 3, because we can depict only 3 dimensions, we need to make sure that we extract out of these 1,000 characteristics the most important 3 characteristics of that object, in order to maintain its meaning and its relevance. Of course, we are losing here precision. If we make this reduction in the dimension of the vector from 2,000 or 4,000 to 3, obviously the precision of representation will decrease, but it is more than nothing, which nothing means that lack of ability to visually represent a vector in multidimensional space. Here is a picture, an example with using UMAP, this technique to reduce the number of dimensions, just to be able to cluster various vectors in a two-dimensional space. Here is
could you explain, Eddie, or the curse of dimensionality, how this reduces it? I'm not entirely clear about the curse of dimensionality. I don't know if you're able to.
Yeah, I'll do my best. So, curse of dimensionality means that okay. So, curse, we know what curse means. So normally we should be very happy that we are able to represent numerically something, an object, in multiple dimensions, because again, based on our finite senses, we're able to represent, let's say, we are able to represent a point in space using 3 dimensions. So definitely this is a constraint, it's a limitation. So we should be very happy that we are able to represent an object, a concept, a word. We are able to represent it in, let's say, 1000 dimensions. So we should be very happy. Well, we are not, because, I mean, on one hand we are, but on the other hand, we cannot use our senses, which is visual, to listen, to hear. We cannot use our senses to perceive this big, high dimensionality of this representation. So it's this representation, high dimensional, lives in an abstract space, which can be, let's say, perceived only mentally using abstract thinking. So this is the curse. So, and now, as I said, we have a word like, I don't know, cat, yeah? So we word the word cat and we represent it using a embedding model with in 1000 dimensions, which means that this cat is described by maximally 1000 characteristics. Yeah. So we say, okay, I want to see this numerical, this 1000 vector. I want to see it. I want to see it. So sorry, we cannot see it because we can see only three dimensions. So okay, which are the most important 3 characteristics of a cat, which are embedded within these 1000 elements? So we need to pick up 3 elements out of 1000, which are the most representative for a cat, and to turn it into X, Y, Z, into a point into this 3D graph. Of course, we lose precision because, but the art of PCA, or the art of this UMAP technique, is to extract, and this is the basically, so the art of these techniques is to extract out of these high dimension characteristics only the most important 2 or 3. Makes sense.
Okay, well, so from my understanding, it's not about humans' ability to understand the data. It's more about the algorithm's ability to work with the data, because when you have so many dimensions, the space and the embedding space in which they exist make it more difficult for an algorithm to determine similarities between different vectors in that space. And in order to do so, you need more data. And that's the curse of dimensionality. As you get to further, if you increase the number of dimensions, then you need more data. And of course, data comes at a premium. That's my understanding of it, but I'm not entirely sure about. I believe because of the space between vectors, because of the large space that they occupy, then it becomes more mathematically difficult to find those similarities. But I'm not entirely sure why. I'm not. That's kind of. I just don't think it has anything to do with the human's perspective on it.
Yeah, I mean, your explanation makes a lot of sense. Definitely, it's a matter of computation. It's a constant. I mean, computation was always a problem. Um,
I'll check into it later, though. Thank you.
yeah. So this is my definitely as the size of tensors increase, the operations become more and more, let's say, uh, complicated and
It
will
has something
consume
to do
more
with
and more
sparsity.
sparsity of resources in general, but also I think for the representation, for the human representation, it's I mean, I think there are multiple dimensions. I think your explanations are more powerful than my simplistic human-related desire to visualize. But yeah. So definitely the size of as the number of dimension increases, also the computational effort increases, the memory footprint, the latency for inference. I mean, it's so. And on the other hand, it's probably as you said, it's. I want to continue your reasoning. On the other hand, it might be a pragmatic human approach, which is Pareto based, when we know that everything or most of the phenomena, most of the reality things follow this Pareto distribution. So we can apply it also for embedding. So because we can say with a high level of competence or trust that the most only a subsection of these dimensions basically depict an object or an word. So all the others are, of course, are uh, bring some additional, let's say, explanatory power, bring some additional, level of details. But at the end of the day, probably we can apply Pareto also to these embeddings. I mean, only 20% of the dimensions carry 80% of the meaning. So it would make sense then to apply PCA to follow your thinking. Yeah. Okay, so why are so powerful? So here the authors are going through all the one-hot encoding techniques used in machine learning. I'm not going to dive into this stuff. Another example, which was approached by the authors, was the to contain this the dimensional into this meaning space of words and images, which I found it interesting. Um, Here an example. I will show you the code real quick. So how the embeddings are created. How the embeddings are created. Basically, there are three ways. Again, I'm going to challenge the authors here because I don't fully agree with them on some ideas. So there are three ways. We can use, say, off-the-shelf embedding models like Word2Vec, for example. I'll show you in the code a couple examples. Then the second approach proposed by the authors is to provide the so-called instruction for these embedding models. And I want to see if I get to the code real quick. Yeah, so let me my collab in a second. Okay. So first model is off the shelf. Yeah, this is an embedding model called the All Mini LM. Let me search for the Hugging Face. Can you see my collab? Can you see my collab? Hello, hello.
No, we still see the book.
Ah, okay. Let me stop and show again. No? Do you see my embeddings for RAG collab?
Yes.
Okay. So this is the first example from the book where the authors used this off-the-shelf embedding model called Mini LM L6, which is placed 105. I will search for the, give me a second to search for the top on Hugging Face. There is a benchmark. If I need to find it real quick. Give me a second. Sorry for that, I accidentally closed my Hugging Face and I need to open it again and to find the benchmark. I'm looking for the benchmark of the embedding models. If somebody can drop me a link on Hugging Face to as I found it. Okay. Can you see now the benchmark?
Yes.
Can you see the benchmark from Hugging Face? I shared the Hugging Face right now. Hello, hello.
Yes. I can see that.
Okay, so here we have a leaderboard for embedding models, the latest, let's say, ranking of the embedding models. And the top number one is Gemini 001, which has a dimension of 3072. The maximum number of tokens is 2000. This is the values for the mean values for all the tasks. I will come back. And here are all the tasks which are for which embedding model can be fine-tuned. So for clustering, for re-ranking, for classification. So there are different tasks for which these embedding models can be fine-tuned. And this top or this ranking shows which are the best in terms of how well they perform across various tasks like classification, clustering, what else here? Instruction, multi-label classification, re-ranking, retrieval, and actually the number one is Qwen. Qwen 3 embedding. This is from Alibaba. They developed, by the way, it's open source, also large language model, very, very well models. I fine-tuned these models, impressive results. So also for the embeddings. So this is the best embedding model which exists today, which has a dimension of 4096, and the maximum number of tokens is 32K. So a chunk can take in 32K. 32K means 2 pages, 2-3 pages of document. Yeah, maybe more. So the size of the chunks is very, very big if we take it as a as a limit or a constraint. And if we look at this clusterment, we see that the example used by the authors is on position rank 105. This is the model used by the authors to show to make the demo. I just wanted to put in context how the embedding model used within this book, where is located, let's say, in this clusterment. Okay, so if we load from Hugging Face's library sentence transformer, we load this model which recommended by the authors, and the authors recommended, or they put here three sentences. Dog sits outside, and the task is to compute the embedding for every sentence and to find what is the similarity search between every between these three sentences. So we have, if we print the embeddings shape, we have three sentences, and in this model, all mini LM has 384 dimensions, so it's a small one. So, and if you print similarities between these three sentences, how can we read it? So, first sentence has a match 100%. So obviously, then first sentence, the dog sits outside waiting for a treat, has a degree of similarity with minus 0.003 with I'm going swimming, which makes sense because these two things are very different. And this first sentence has a similarity of 0.2 with the third sentence. So the dog sits outside is positively related, or with the third sentence, which is the dog is swimming. It's about the dog. Then for the second line, we read the second sentence. The similarity, the sentence with the first one is minus 0.003, the same like here, is 1 because it refers to itself, and 0.3 with the third one. I'm going swimming with the dog is swimming. So there are some correlation between the person and the dog which are swimming. So if we, so this was the how the embedding is calculated. As you can see, it's super trivial, and how the similarity is computed. Now for the text, original code from the authors. So if we run the code, so basically here is a cat, and we want to see what, first we need to embed the cat, this picture actually, and then we need to see how this picture is what are the similarity with these three sentences: a crazy cat smiling, a white and brown cat with yellow bandana, and a man eating in the garden. So the correlation between the picture and these three sentences, or is depicted in this tensor 0, 3, 0, 3, and 0, 1. And how we should read it, it's a more related to, let's say, a relative, it's a relative ranking, which means that the picture, I will show you the picture. Maybe I should go to the picture. Here I made some visual representation of this code, and I run again the code, and these are the sentences. So basically, this is the image from the GitHub, and these are the three sentences. So we can see that the highest correlation, the highest similarity between the image and is with this sentence that it's a white and brown cat. And it has a very low similarity with a man eating in the garden. Okay, so this was the embedding for the pictures and words. I'm coming back with please let me know if you see my Kindle again. If somebody still on the call. Okay, last part is this vector database, which performs within the retrieval process performs approximate nearest neighbor algorithms in order to find the close neighbors, and which means that the answers will not be always 100% accurate. It's an approximation by definition. And the workflow within the database, the vector database, is as follows. First, the vectors are indexed using various algorithms, and then various operations in the database are taking place, like sharding, replication, monitoring. And so this concludes the naive RAG architecture. If there are any questions, or if we can move on to advanced real quick, or we are actually on the, it's a little bit late. Any questions so far?
No, this was pretty thorough.
Sorry, yeah, I have one question, which is about the multimodality, basically. I guess the embedding model that
I
was
cannot
used.
hear us.
Yeah. Sorry.
Sorry, can I repeat? Say.
Yeah, I was saying that my question is about the multimodality on the embedding model. In particular, we have this example in which we pass the model a picture, and it gives us a vector that is more or less compatible with another embedding, which is starts from sentences. And I guess my question is that probably was made by creating the embedding model, the one that reads images after the other one, so that you train it to see images and generate the embeddings that the other model generated? Because it's like kind of a coincidence, like how do you make the image to have the same embeddings as the text? So I guess the idea is that they before they generated a model passes from text to a vector, which is something that we have seen in Sebastian Raschka book. And then once you have those those embeddings, then they took the model that reads an image, and from that they trained the model so that it outputs for certain images, like for instance the cat or whatever, and they force the model to learn how to generate the images that would have been embedded by the text model.
How I read it, so basically the teacher is turning into an object which is projected within the same similarity space as the text.
Yeah, exactly, yeah.
So it's like the logic or the requirement we discussed for the user query and embedding we need to apply for the chunking. So the user query must go to the same embedding model like the chunks within the database. So because the embedding model creates the conditions to have a single semantic space. And in this semantic space, we can have all the modalities. We can have words, audio, and video, and images. So as long as we project all these modalities within the same meaning space or semantic space, then we'll be able to compare and to see which are the similarity between video and text or whatever. So basically, we normalize all the data types using the same logic, using the same embedding model. But again, what I wanted to also to emphasize is that I think it's better to. So I don't agree with the authors. It's better to fine tune an embedding model, because if you fine tune an embedding model, that model will know the jargon within your domain. So and all the domains have jargons. All the domains have jargons. Yeah. So in order for a large language model to, for an embedding model to understand these nuances within a domain, it must be fine-tuned for a given domain, not instruct, not default. So I tested instruct. If you want, I can show you some tests because the authors suggest that we should use instruct embedding model. It's not working. I mean, it's working very, very poorly. So because instruct basically is like a kind of prompting for the embedding. So the idea is to control the quality of the similarity searches or similarity meaning using a kind of prompt, so called instruct, but it's not working. So the best solution, I think, it's fine-tuning embedding models using your own domain data set. Otherwise, and I tested also. I want to say that I tested Kuver, this model from Alibaba. It's incredibly crazy. It's so good. This Qwen 3 model. I tested 4 and 8 billion parameters. It's very, very good models. Very good models. Very accurate. I would probably better probably than OSS 20 billion from OpenAI, which I tested also. So the bottom line is that from again, and also this book is a good example for me, is that the best solution is to test. The best solution is to test and to verify various models. I did it. I don't have time. If you want, I can show it next time. I tested several embedding models to see which one is more, let's say, precise in embedding meaning of these sentences from this book. I also use instruct as the authors recommended, and the results were very bad. So I mean, testing is the best strategy. Testing, just do it and see what works, see why something works. But again, the lessons which I learned, say, over the years, after reading lots of books and papers and stuff, is that you need to do it by yourself and to apply your own filters and your own thinking. And yeah, so this is my takeaway from this presentation: do yourself and challenge everything.
To that question about how is it, that you just had about how are they aligned an image embedding space with a text embedding space. The way it's done is through the captions in the image. The image is transformed into an embedding space using something like a convolutional neural network, where the text is transformed using attention mechanism. But because the image has a caption, then the way that embedding space points would be similar to the caption, the way the text would point. And so there's a similarity between those embedding spaces, and that's how it's done. That's the answer to your question. It's not done without the help of text to guide it, in other words.
Yeah, you're right. Yes, you're right. Yeah, Chris is right. So yeah, I should have mentioned that without the caption, yeah, obviously, without the caption cannot work. Basically, the data, the raw data from we need a look to it, and then based on that label, we can extend the similarity to sentences.
Does anyone have more questions?
Yeah, kind of off topic, Eddie. I'm curious to hear your thoughts on the embedding space and the philosophical aspect of it. You were kind of alluding to it, and I find that fascinating as well. So I'm interested to hear what you were alluding to.
Well, there are some. We can stop the recording because we enter into a non-technical space now. I don't know if Carlos, you have. One second to find the name of the guy which is writing right now PhD under the supervision of Jordan Peterson about how using large language models we can define sacred concepts. I'll share the link. It's very cool.
I remember a game. I don't know if you have seen it. There was a game online. There is probably the webpage still around. It was a game where you thought it told you something like, think about one person, about the entire history of humanity, and even fiction characters. Just think about one, whoever you want, and then it made you. I don't remember how many questions, but it was just making you binary questions. But it was like 6 or 7 questions, and it always was able, just with 6 or 7 binary questions, it was able to guess the character that you have in your mind, because it was gonna ask you, is it woman or man? Is it alive or dead? Is it fictional or and in a few questions, I don't remember how many, it was able to guess from a very, very big list of obviously possible solutions. And I guess that it was more or less, I mean, it was not AI, it was before neural networks, but the idea behind representing something with numbers in a vector, I think that it's kind of related, because it's like you can abstract features into dimensions, and just with numbers, if you keep adding numbers, you can represent things like you can more complex definitions just by adding features. So kind of the intuition, I always take it from there.
Yeah, and from the philosophical point of view, to answer to Chris' question, is that using numbers, we can get to the deepest level of reality, or one of the, probably not the deepest, but one of the very deep levels of reality, and which means that the construct or the meaning of a word, of a concept, hierarchical structure of several abstract meanings, which can be ultimately represented in words and in numbers, in a vector, in the multidimensional vector, which means that in order to make the similarity search between two different concepts, if we are able to describe these concepts using these multidimensional vectors, basically we are able to decompose these multi-level abstractions of what represents a concept into the most fundamental number, and then to be able to compare the vectors and of course the meaning and what is the overlap between the various concepts and how similar, how not similar they are, etc. Based on this approach. So this is how I think it can help also the philosophical level to better understand the most fundamental life constructs, which is, for example, purpose or meaning, or so there are things which are very deeply rooted, let's say, in philosophy, which can be addressed now by large language models. And again, it's a guy which I'll share later if I find his name, which has a PhD or writes a PhD exactly about this topic. I hope, Chris, I answered your question.
Yeah, I was just curious what your thoughts were on it. Thank you.
Yeah, so in one sentence, I see it as I see, let's say, the most fundamental concepts of reality as depicted as represented as several layers of abstractions, which until today we were able to express them, let's say, using books, using philosophers, etc. And I think now we can represent them numerically, and we can test if something is similar to something else just based on the similarity, mathematical similarity, in terms of the most fundamental concepts. So I see some comments here about about, yeah, it's a good description here about I'm not sharing about the Elan shared with the CDC. Yeah, definitely. Yeah, so my comment, yeah, I didn't check this Confluent link, Patrick. How I see his book, I see it as a framework. I mean, I would use, let's say, just to provide a kind of guideline. But I think it's up to every particular use case how we design this this architecture. Okay, so I think Carlos, based on the complexity of this topic, chapter 4, I would say that minimum another session will be required next week. Minimum. It's a big topic, and it's important as well. Yeah.
But do you want to also make the next session or leave it for anyone else?
I don't know if I will be available next Sunday. So I have some guests coming in Germany, and I don't know if I'll be able to join at all.
Okay. Anyone wants to volunteer? So we would be doing more or less. Where did we leave it? Embedding. Maybe from the pedantic domain entities, or where would you say that we should start the next session?
So I would continue with advanced RAG. It was basically advanced RAG represent the production RAG. So as I said, we cannot run in production naive. It's simply it's not working. So advanced RAG is a topic in itself. So I think it worth it. I don't know, at least 30 minutes. Advanced RAG, and I would say that for advanced RAG, an example should be given. I mean, working example of how advanced RAG works. Because again, advanced RAG is what actually works in production. And within this book is just a couple of pages, and the authors are working over this topic very easily, in my opinion. But I think advanced RAG worth a lot more attention, and because again, if somebody wants to deploy their own RAG architecture, advanced RAG will be the answer. So this would be one, and then implementation, the effective implementation of twin feature pipeline would be also another session. But again, for practical reasons and pragmatical reasons, I would say advanced RAG must be dedicated for a real use case, not necessarily from this book.
Okay, so if we don't have other volunteers, I will pick it from here for next week. And I think that's it. So thank you very much, Eddie. I'm kind of leaving because now we have the beginner session. So also if anyone wants to join us, we'll be in the other event on the other channel. So thank you very much, Eddie. Very good session.
Yeah, thank you. Okay, guys, have a nice Sunday.
Yeah, you too.